Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that in the previous class we had worked on extending the Hamilton-Jacobi-Bellman framework, and we look at some examples, and then we have started off talking about the single period optimization using the Martingale or the duality approach. And in today's class we will continue our discussion on this by looking at a couple of examples, and then we will talk about the multi-period setup in case of the Martingale approach for discrete time, and then we will talk about what we are going to talk about is going to be the continuous time setup, and in the continuous time setup we will look at the Martingale approach in order to decide on what is going to be our optimal portfolio. So, accordingly we start this lecture by recalling that z of 1 was defined as u prime of x hat of 1 over the expected value of u prime of x hat of 1, and this is u prime of x hat of 1 over lambda. So, for some lambda. So, I can represent z1 motivated by this form to be written as u prime of x hat of 1 over lambda for some lambda. So, we begin with defining the inverse function of u prime as I of z is equal to u prime inverse of z, and therefore, we have x hat of 1 is equal to I, that is the inverse function of lambda of z of 1. Now, if we can find this parameter lambda, then we know. So, here if we find the lambda, we already know what is z1. So, we can calculate I of lambda z1. So, the determination of x hat of 1 then reduces to finding of lambda. So, accordingly then we know the optimal terminal wealth, and thus we can compute the optimal portfolio that attains it, and by it I mean that attains x hat of 1. So, in conclusion, the optimal delta hat, which is the optimal holding in the stock, and lambda, which in turn will give you your x hat of 1, can be obtained from x hat of 1 is equal to delta hat of s of 1 plus x minus delta hat of s of 0 into 1 plus r. So, remember that x hat of 1 is going to be delta hat of the stock price at time 1 plus x minus delta hat s naught, that is the investment in the bond, grown by a factor of 1 plus r, and this is from this relation, this x hat of 1, which is this expression, must be equal to I or the inverse function lambda into z1, and this is nothing but a system. Remember that z1 has two values and s1 has two values, and accordingly x1 has two values. So, this gives is a system of two equations in two unknowns. So, let us now look at an example. So, the question is that using the Martingale approach, in the single period binomial model, find the optimal strategy for maximizing the expected value of log of x1, that is for log utility function. So, what I am asking is use the Martingale approach to find the optimal strategy with log utility and power utility for a single period model. All right. So, for gamma less than 1. So, the solution is as follows. We have to replicate, and by replication we mean that we have to get lambda such that x set of 1 is equal to I lambda z 1. So, that means we have to figure out our delta hat and lambda in such a way that this condition is satisfied, and this must be done for an appropriate value of lambda. All right. So, in particular we have I of lambda z bar u, and I will explain what is z bar, is equal to delta hat s naught u plus x minus delta hat s 0 into 1 plus r, and I of lambda z bar of d is equal to delta hat s 0 into d plus x minus delta hat s naught into 1 plus r. Okay, so now recall that we had the expression for ZU and ZD determined in the previous class. So, ZU was 1 over p into 1 plus r s 0 minus s superscript d and su minus sd, and zd is equal to 1 over 1 minus p su minus 1 plus r into s 0 over su minus sd. So, note here that this s 0 of u is nothing but su, little s of u, and s 0 of d is little s superscript d. So, now here we have used the notation z bar u and z bar of d. So, accordingly note that this notation z bar of I, where I could be u or d, this is z superscript I over 1 plus r. So, basically this is the discounted value of z. We also introduce the notations. So, apart from this notation, we also introduce a couple of more notations, which will be u tilde is u minus 1 plus r. So, that means this and this combined will give you delta hat s naught into u minus 1 plus r. So, that u minus 1 plus r I will denote as u tilde, and accordingly for the second one we will have d minus 1 plus r, which I will denote as d tilde. Okay, so, now for the utility function being the log utility, as is the case with the first part of the problem, what is u prime of x? U prime of x is equal to 1 over x, and this implies that the inverse is going to be 1 over z. So, inverse function I of z becomes 1 over z. So, once you have this, so once you put in the expression, so I of z is equal to 1 over z. So, accordingly this term is going to be 1 over lambda z bar of u, where z bar of u can be obtained from here, and accordingly here also I will get 1 over z lambda z bar of d, where you will get z bar of d by making use of this relation. So therefore, we will get that we get these two equations, this and this here, and you can use these two equations to solve for lambda to get 1 over lambda is equal to 1 x into 1 plus r into d tilde minus u tilde, where u tilde and d tilde have been defined here, divided by d tilde over z bar of u minus u tilde over z bar of d. And accordingly, you will get delta hat as 0, that is your optimal portfolio. Delta hat is obtained from the relation that delta hat of S0 is 1 over u tilde within bracket x into 1 plus r minus 1 over lambda into z bar of u, where lambda 1 over lambda has already been determined here. So, this was the first problem. Now, for the second problem, in case of the power utility, that is x raised to gamma over gamma, we have what is going to be I of z. So, this is going to be z raised to 1 over gamma minus 1. So, for here you notice that u prime of x is going to be gamma x raised to gamma minus 1 into gamma, and call this some y. So, that means x is going to be y raised to 1 over gamma minus 1. So, actually let me call this as z, and this is nothing but I of z is going to be equal to z raised to 1 over gamma minus 1. So, for this we obtain that lambda raised to 1 over gamma minus 1, this turns out to be x into 1 plus r into d tilde minus u tilde over d tilde z bar of u 1 over gamma minus 1 minus u tilde z bar of d raised to 1 over gamma minus 1, and you get delta hat S0 is equal to 1 over u tilde x into 1 plus r minus lambda z u bar raised to 1 over gamma minus 1. So, this is going to be your lambda, and this is going to be your consequent portfolio delta hat given by this relation. So, in both the cases we have obtained the delta hat in terms of lambda that was obtained in the previous step. We next now move on to from the single period model to the Martingale approach. In multi-period binomial model. So, let us start off with the observation that motivated by the single period model, we have to identify a random variable zt, z of capital T, such that the following condition holds. So, I am just going to extend the condition that, so earlier what we had? We had E of z of 1 over 1 plus r into s of 1 was equal to S0. Now, z1 over 1 plus r, this can be written in the form of E of z bar of 1 into S1 is equal to S0. So, motivated by this, we now take expected value of z of t, and now this, instead of dividing z1 by 1 plus r, I can divide this by I can divide S1 by 1 plus r. So, in which case this form is going to be z of 1 into s bar of 1 is equal to s of 0. So, motivated by this form, we get that E of z t into S bar of t is going to be equal to S 0, where this newly introduced notation S bar at any generic time little t is given by S of t over 1 plus r raised to small t. Further, we hope to find a stochastic process z of t such that E t of z t is going to be z of little t with z of 0 being equal to 1. And the other relation is E t of z of t S bar of t, this is going to be z of little t S bar of little t for all t less than small t. So, let me call this equation 2. So, therefore, we want z of t to be a martingale as well as the process z t S t to be a martingale. Remember, we had introduced the definition of martingale in the previous class. So, in particular, expected value of z of t into x bar of t, this is going to be the expected value of z bar of t into x of t is equal to little x. Let me call this equation 3 with, of course, this little x is nothing but the initial wealth level x of 0. Now, we note that the expected value of z of t and x into x bar of t, this is going to be the expected value. So, I can write z of t to be the expected value of t minus 1. So, here expected value of t minus 1 into z of t into x bar of t. So, this is going to be delta of t minus 1 into s bar of t. So, I am basically writing the discounted wealth process. So, this is going to be delta of t minus 1 s bar of t plus x bar of t minus 1 minus delta into t minus 1 into s bar of t minus 1. Where the newly introduced notation of delta of capital T minus 1 is the number of stocks held at time capital T minus 1. Now, since the expected value of E of t minus 1 of z of t delta of t minus 1 s bar of t minus 1 is equal to the expected value of z of t minus 1 delta of t minus 1 into s bar of t minus 1. So, by equation 1, and if 2 holds, we get expected value of z of t into x bar of t. This is going to be z of t minus 1 into x bar of t minus 1. And continuing in this manner, we get relation 3. So, eventually we will go to z of 0 which is 1 and x bar of 0 which is going to be equal to just little x. So, that is how we end up getting this relation. We now consider equation 3. So, that is this equation here, this as a constraint. For our problem of maximization of the expected terminal wealth. So, this gives the Lagrangian of expected value of the utility of terminal wealth minus lambda into the constraint, that is the expected value of z bar of t into x of t minus little x, where this lambda is the Lagrange multiplier. Not to be confused with the lambda that we had done earlier. Now, now you want to basically solve the optimization problem using this Lagrangian. So, taking the derivative with respect to x of t and setting equal to 0, we get the expected value of u prime of x hat of t minus lambda into z bar of t equal to 0. So, in particular this condition will be satisfied if we can find a portfolio strategy such that, so from this relation we get the condition that x hat of capital T is going to be the inverse of lambda z bar of t, where I of course is the inverse of u prime. So, I is against the inverse function of u prime, and remember that u prime is nothing but the marginal utility. Further, from 3, lambda has to satisfy which relation, that E of z bar of t, and for x of t we have this relation I of lambda z bar of t, and this is going to be equal to little x. Accordingly, lambda will be determined uniquely by this equation, that means this equation. So, in summary we can state the following, that in the binomial model the optimal strategy is the strategy that replicates the claim I of lambda z bar of t with lambda and z of capital T being obtained as outlined above. So, this brings us to the last topic of the duality or the Martingale approach in continuous time. Let us consider the Black-Scholes-Merton framework, and by this mean that is a continuous time model and the portfolio comprises of a stock and a bond. So, accordingly this Black-Scholes framework comprises of one stock and one bond. Also recall from our discussion on the HGB equation that theta is equal to mu minus r over sigma. So, I am just recalling the notation since I am going to use this now. So, we now introduce the stochastic process which I will define as z of t. So, this is basically the same z as before, but in the continuous time setting is given by e raised to minus theta into Wt. Remember, the asset price is follows the geometric Brownian motion minus half theta square of little t. And this process is called the risk neutral density. So, this is some sort of a the equivalent of the z that we had in the discrete time case. So, you can show that using Ito's lemma. So, Ito's lemma is nothing but the Taylor series expansion in the world of stochastic calculus. So, an application of Ito's lemma, this gives dz. So, just like you obtain dz in the deterministic case using Taylor series. So, in the stochastic case we have Ito's lemma which gives dz is equal to minus theta z of dw of t with z of 0 being equal to 1. So, z 0 equal to 1 you can see from here that z of 0 will be e raised to w of 0 will render this term 0 and t equal to 0 will render this term 0. So, z of 0 is going to be simply e raised to 0 which is equal to 1. Also z is a martingale, and I will just make a brief note without actually proving why this is a martingale with expectation equal to 1. So, regarding the expectation being equal to 1, you can actually calculate the expected value of this and use the probability density function for the winner process Wt, which is the normal distribution. And the other claim that I have made here is that z is a martingale and equal to 1, and for this we just make a note that this modification that is using the Ito's lemma results in a process without drift. So, without drift basically means that, as you remember that we had ds is equal to bus dt plus sigma is dw of t, and this term was known as the drift term. So, drift term is the term which has dt. So, since this does not have a dt term, so it that means you have obtained a process without the drift that is only has the component dw of t, and therefore, under some conditions. So, because of the absence of this drift term, so under some conditions this is a martingale. Now, x bar of t, what is this? So, x bar is basically the bar will denote the discounted process. Now, x bar of t means that it is a discounted process of x of t, and now since this is a continuous time setup, so the discounting factor is going to be e raised to minus r t. In the discrete time, this was x t over divided by 1 plus r raised to t. So, for discrete time, x bar of t would be x of t over 1 plus r raised to t. So, the equivalent in the continuous time setting is going to be this form. So, this results in the relation d of z x bar is equal to z bar into pi sigma minus theta x into dw, where x is basically the wealth process. Or if you integrate this, what will you get? If you integrate from 0 to little t, what is this going to give you? This is going to give you z of t into x bar of t minus z of 0 which is 1 and x bar of 0 which is equal to x, and this is going to be integral 0 to t z bar of u into pi of u sigma minus theta of x of u into dw of u. Or equivalently we can just write this as z of t into x bar of t is equal to x plus integral 0 to t z bar of u, let me just rewrite this, pi of u sigma minus theta of x of u into dw of u. Now, you observe that here we only have the dw term and there is no dt term. So, this means that z x bar is a martingale, again provided the integrand, that is this term here, this satisfies some conditions. Now, since z of x bar is a martingale, so as a consequence we get that E conditional expectation of t of z of t x bar of t is going to be z of t into x bar of little t, where this newly introduced expectation E subscript t is the conditional expectation conditioned on the information available at time t. So, accordingly, the self financing condition results in, so that means at t time little t equal to 0, this results in the expected value of z of t into x bar of t, this is equal to little x. So, accordingly, we now have to solve the following problem. That supremum of expected terminal expected utility of the terminal wealth over x of t subject to the expected value of z of t x bar of t, this is going to be equal to little x, and this is equivalent to solving the optimization problem of supremum. So, I am defining the Lagrangian supremum of u of x of t minus lambda into x minus expected value of z of t into x bar of t over x of t and lambda. So, differentiating with respect to x of t and setting the derivative equal to 0, we get u prime of x hat of t, and I am using x hat because now the differentiation has already taken place. This is going to be equal to lambda of z bar of t for the candidate x hat of t for terminal wealth. So, if I of y is defined as again as u prime inverse of y, then from this relation we obtain that x hat of t is going to be equal to the inverse function of lambda z bar of capital T. So, let me just summarize the continuous time discourse. So, here the optimal wealth is equal to the inverse of the marginal utility evaluated at the discounted risk neutral density. Remember, z of t is the risk neutral density. So, z bar of t is the discounted risk neutral density multiplied by lambda. And the condition is that we have to choose lambda such that what was the other condition? The other condition was if we took the derivative with respect to lambda, we recovered this condition. So, accordingly, we need to choose lambda such that expected value of z bar of t. So, we have this z bar of t. So, I can switch the z bar into x of t. So, this expression is going to be z bar of t into x of t, and I can replace this x of t from here to obtain expected value of z of t into I of lambda z bar of t, and this must be equal to x. All right. So, this means that you figure out what is the lambda making use of this relation. So, this means that you make use of this relation to figure out what is lambda and then substitute the lambda to obtain what is x hat of t. So, this brings us to the end of this lecture. So, just to do a brief recap, what we have done in today's lecture is we looked at an example of the single period optimization using the Martingale approach and gave the setup for the multi-period optimization, and then we moved on to the continuous time framework and gave the approach using martingales in order to find what is going to be the optimal portfolio. So, this brings us to the end of this module on optimal portfolio and consumption, and from the next week we will start off with a new topic, namely on bond portfolio optimization. Thank you for watching.